Alright, welcome everybody, welcome to another video. So in this video we're going to deal with a very popular problem in graph. This problem asks you to count the number of paths between two given nodes, u and v. Let's say here between two nodes that are 0 and 6. Okay, how many different paths, how many different ways, how many different routes can we take in order to go from 0 to 6. Okay, so the number of different ways, the number of different paths could be counted using the depth first search algorithm. As I mentioned in the previous videos, the depth first search and the breadth first search are the skeletons of most of the algorithms of graph. So if you master depth first search and breadth first search, all the remaining algorithms will be some variation of those two fundamental algorithms. So the number of different paths here doesn't have cycles, of course. So if we visit some node 5, then we cannot revisit 5 again. Okay. So in other words, there must be no cycles in there, because if there were cycles, then the number of paths between two nodes would be infinite. Okay. Since we are interested in a finite value, we do not visit a node more than one time. All right. So here's an example. What are the different paths from 0 to 6? So actually there are 6 paths, and here they are. You can go from 0 to 1, then from 1 to 2, 4, 6. That's one possibility. Here's another possibility. You can go from 0, 1, 2, 5, and 6. Here's another one. 0, 1, 2, 5, 3, 7, 6. And here's another one. 0, 1, 3, 5, 2, 4, 6. Here's another one. 0, 1, 3, 5, and 6. And here's the final one. 0, 1, 3, 7, and 6. So these are the different paths between 0 and 6. Now the problem is to find how many. So in this example, it's 6. Okay, for much bigger graphs, much larger graphs, it would be very, very, very hard to do that with hand. For that reason, we are interested to make a program which will do that for us. Cool. Now, since this algorithm is based on top of a depth first search algorithm, it'll be something like this, its function. So let's call it NB paths, which stands for number of paths, and it has a starting vertex, that's u, and a target vertex, that's v. So we are interested to find the number of paths between that u and that v there. And of course, let's give it the visited array, because this will use the visited property. Okay? So as you can see, when I illustrated the examples of the paths, whenever we go through a vertex, we don't go through it again. We don't make any cycles. Here, for example, we go from 0, 1, 2, and then 4 to 6. 2 is visited, right? But one of the other paths will pass through 2. So that's 0, 1, 2, 5, 6. So both of them pass on top of 2, right? So the visited and unvisited property is not static. Okay, it'll be updated during the execution. And actually, whenever we visit a path, whenever we visit a node, whenever we pass through it, we make it visited, and when we leave it, we make it unvisited. Okay, we mark a node when we visit it, and when we quit, we unmark it, so that for the next path it could be considered. All right, let's write a simple algorithm that will do this. So the first thing we said is basically to mark u, to make it visited. And then we're going to visit all the adjacent nodes of U that were not marked. So visit all adjacent vertices of U that were not visited or marked. Okay, and then finally we unmark U. So we mark U, we visit it and all of the nodes after it recursively, and then when we quit it, we basically unmark it. Okay, and here's the base problem. Since this is a recursive function, it must have a base problem, a problem that shall make the recursion stops. So the problem here, the base problem would be when U equals V, when a graph, when both U and V are talking about the same node. Okay, so for example, if you have a node here, a graph that has one node, then how many different paths to go from that node to itself? Well, there's only one path. You can visit this node only once. Okay, so that's the base problem. When U equals V, then we're just going to return 1. We're going to stop the recursion. So if both U and V are equal, so if U equals V, then in that case we're just going to return 1. There is one path from U to itself, from 6 to 6, there's only one path. Otherwise, we're just going to visit all the adjacent nodes of U. But again, for every node we visit, we have to take its value and add them up. We're just going to add all of the values together, all of the values of the subproblems. So we're just going to create a variable S that will contain that sum, which will start at 0. And for all of the nodes that we visit, every time S will be incremented by the returned value of a function call. So we call the first adjacent node, and then we add its return value to S, and then we call the second adjacent node, and then we add its return value to S, and so on and so forth, until we've completed calling all of the functions, all of the nodes that are adjacent to U, and then their sum is stored at S, so finally we're just going to return that S. Okay, so that's the principle. So let's execute this algorithm on this test. So basically the first thing that we're going to do, we're going to check if U equals V. We're going to start with U equals 0. So 0 is different to 6. So let's say V is 6 here. So U is different to 6, 0 is different to 6. So we're just going to mark U. So let's do that. And then our S here will be 0 initially, and then we're going to call all the adjacent nodes. So the first adjacent node and the only adjacent node is basically that 1 there. And the same thing, 1 is different to 6, so 1 will call all of its adjacent node. So the first adjacent node is 2. And then 2 will call its adjacent node, which is 4, and then we'll call its first adjacent node, which is 6. Now 6 equals 6, so that will return 1. So that will unmark the last node 6 there, and that will return 1. Cool. Now 4 doesn't have any other subproblem to call, so its S will contain that 1 and that 1 only. So it'll return it. It'll return S, it'll return that 1 there. Okay? Cool. Now 2 have called its first subproblem, which is 4. Now it has to call its second subproblem, which is 5. So it'll call 5. Since 5 is not visited, it's going to color that, And then the same thing happens for 5. 5 will call its first subproblem, which is 6. So it'll call 6. And then 6 equals 6, so that will return 1. Okay? And again, 5 has another subproblem, which is 3, so 5 will call 3. And 3 has another subproblem that we're not visited yet, which is 7, which again has another subproblem, which is 6. So 6 equals 6, so that will return 1. So this is 1. And then 7 will return that 1 since that's the only content of its S. So that's 1 there. And then 3 have called all of its subproblems. It has called all of its subproblems and it'll return their sum. So that's 1. Their sum is 1. So it'll return that 1 there. And now 5 will take the sum of its subproblems. So we have here 1 plus 1, that's 2. So 5 will return 2. Cool. Now back to the 2. And of course, whenever we leave a function call, we're just going to unmark it. Here I forgot to unmark these. So 5 will be unmarked also. And we're back to the 2. So the 2 will take the sum of its subproblems. 1 plus 2, that's 3. So the 2 will return 3. And of course, it'll be unmarked. And now the 1 will call its second subproblem, which is the 3. So it'll mark that. And again, the 3 will call its first subproblem, which is 5, which will call its first subproblem, which is 2, which will call its first subproblem is 4, and then 6. Now 6 will return 1 because 6 equals 6. And then that 1 is the only subproblem, the only returned value for the subproblems of 4, so it'll return it and unmark itself. So this will return 1. And then we're back to the 2 here. Now the 2 has its only subproblem is 1 there, so it'll return it. So it'll return that 1 there and gets unmarked. And then 5 will call its second subproblem, which is the 6. The 6 here. Now the 6 will return 1 because 6 equals 6. So 5 will take the sum of those two subproblems, 1 and 1. So 1 plus 1 equals 2. So the 5 will return 2 and will be unmarked. The 3 has called its first subproblem, so it has to call its second subproblem, which is the 7. So it'll mark the 7. The 7 will try to call its subproblem, which is the 6. 6 equals 6, so this will return 1. And the 7 has only one subproblem that returned 1, so its S is 1, so it'll return that 1. And it'll get unmarked. Now we're back to the 3. Now the 3 will take the sum of its subproblems. That's 1 plus 2, that's 3. And then it'll get unmarked. And then the 1 has executed all of its subproblems, so it'll take all of their sums, so that's 3 plus 3, so that's basically 6. And of course it'll get unmarked. And now we are back to 0, so we will return its only subproblem, which is 6, and it'll get unmarked. And by that, we have visited all of our graph using depth-first search, and we have counted all the different paths, how many different paths to go from our start to our destination. Alright, that's it for this video. For the implementation, check out the next one. See you then.